So here we go.
Search and destroy.
Yeah, search and destroy. Oh, I mean search and sort. So first of all algorithms we use with regular arrays can be used with array lists. You know, by algorithms I mean, you know how we were like, find the maximum, the minimum, and the average, you know, where you go through the whole thing. Or a linear search. Or go through the list and change everything. These are all things you can do. You can do the same things with array lists as you can with arrays. So we're not going to do them all. Today I'm going to have you code a linear search. Today... And a linear search, I'm asking you to write a method that returns the index of the thing you're searching for. So it's just standard search. Linear search, remember, means start at the beginning and just go through and check every item and see if the thing you're looking for is there. I mean, as humans, we're happy that we don't have to do a linear search every time. Imagine coming up to a bookshelf and you have to start at the top left and you have to go all the way across the top shelf and then go to the second shelf. And like you might know, you might even just be able to see, just, oh, look, that blue cover I'm looking for, it's on the fourth shelf over on the right. You just go and grab it. That's not a linear search. That's some sort of intelligent search. I don't know what you would call that one. But computers can't just, oh, I see it over there, you know, like, I mean, unless they're set up to be doing that. So we're going to code a linear search with an integer array list and also with a string array list, two different ones. Not a big deal. Today, though, we're talking about sorting. And I want to read you guys a little bit out of a book. I got this book, you know you're a nerd when family members give you books titled Algorithms to Live By. My sister got me this book, and...
you take notes in it?
No, I flagged the places I wanted to read to you. There's a whole chapter on sorting, and so if you just listen... we're just going to have to drop in the middle of something. But they're talking about how sorting is a huge challenge. So, to lower cost per unit of output, people usually increase the size of their operations, wrote this guy Hoskins in 1955, in the first scientific article published on sorting. So 1955, first time somebody wrote an article about sorting. This is the economy of scale familiar to any business student. So you guys know economy of scale. You're like making these little widgets. And lots of times, if you're making 100 widgets, that's more expensive per unit than if you're making 1,000 widgets or 10,000 widgets. It depends on what you're making. But lots of times they talk about economies of scale, like, hey, let's build a big factory and let's lower it so the cost per unit of our building it is way lower. With sorting, it's exactly the opposite. The larger the data set you're sorting, the more costly it is. So it says, but with sorting, size is a recipe for disaster. Perversely, as a sort grows larger, the unit cost of sorting, instead of falling, rises. Sorting involves steep diseconomies of scale, violating our normal intuitions about the virtues of doing things in bulk. Cooking for two is typically no harder than cooking for one, and it's certainly easier than cooking for one person twice. But sorting, say, a shelf of 100 books will take you longer than sorting 2 bookshelves of 50 apiece. You have twice as many things to organize, and there's twice as many places for each of them to go. The more you take on, the worse it gets. This is the first and most fundamental insight of sorting theory. Scale hurts. All right, I'm going to hop to another spot. They spend pages talking about the effort required to get certain things done, and whether the effort is a constant or a linear function or a quadratic function. So what they propose is an example of a constant time sink job is you're going to clean the house. And if you're going to clean the house thoroughly, there's a bunch of things you're going to do. And sure, it might take 5 minutes less or 10 minutes less or 10 minutes more if it was dirtier. In general, if you're going to clean the house, you're going to clean the bathrooms, you're going to vacuum, you're going to do this stuff. Cleaning that house is going to take that amount of time all the time. That's a constant amount of time. Let's say you were at a dinner party and you were going to pass around a salad. It's going to take a little longer if there's 10 people at the table than if there's 5 people at the table, right? So every person you add is just going to get a little bit longer. That's called a linear overhead. You know, you have 2 people, 3 people, 4 people. Every person you add, passing the dish around the whole table is going to take a little bit longer. But it doesn't get crazy longer. Whereas with sorting, they call it a quadratic problem. So if you had 10 items, if you had, it'll take a certain amount of time. If you have 20 items, it takes more than twice as long to sort. Probably. It depends on your sorting algorithm. Think about this. An example they give is if you have 52 cards in a regular deck of playing cards, the number of ways those cards can be organized is 52 factorial, which is, they list the number over here, but I'm not going to read it. But it goes on at 2 lines, and it's as wide as the text. It's just all numbers. It's got 67. It might as well have 67 zeros. You know, it's a hell of a number. So imagine you think I'm just sorting 52 things. Well, there's a lot of ways those things could be arranged, and it takes a lot of work to. Yeah, exactly. So most sorting algorithms are in the quadratic world. There is one sorting algorithm we're going to learn about. We're not going to have to code it or even look at the code for it. It's called a merge sort that lowers it to somewhere between linear and quadratic. It's actually logarithmic time. Yes?
What about quick sort?
It's quadratic. All those sorts. Okay, but we're going to learn 2 sorting methods today. Our 2 insertion sort and selection sort. So I'm going to describe how these work. I'm not going to make you code them. I was going to, and then I was looking on the AP Classroom, and they just put the algorithm in one of the questions. Here's a correctly functioning insertion sort. Now tell me how many times line 12 gets executed. You know, so you have to follow the code and look at it. But I think I would like to have you code it another day, but I didn't want to do that right now. So let's talk first an insertion sort. So I'm going to go to a new line. So this would be the same if it's an array or an array list or any ordered list of things. So So we go forwards through the list, starting at the second item in the list. We assume the first item is already sorted. In other words, you'd start at I equals 1 instead of I equals 0. And then check if the current value is less than any value before it. So you go backwards and check. In this case, at the very beginning, there's only one item before it. So you say, hey, is my current value, the item at spot 2, is that less than the item at spot 1, at the first spot? If it is, you put the current item in that spot and you bump everything over one. You insert and you move everything over. So if you find a place where it should go, insert it there, moving all other items up one. It's not all other items, it's all other items up to the point you're working on. I'll show you a very specific example in a second. Then go to the next. And you go to the next item and repeat. It's hard to put these in words, so don't worry. I'll give you an example. Let's do just no. Let's do yeah, that's fine. Here's our little list. We got 3 numbers in it. So what we do first is we're looking at the 2. And you would have a loop in your code that went back to item 0, checking every item before the current item to see should the current one be before any of these things? And if it should, you put it there and move everything over that needs to be moved over. So in this case, we would end up with the 2 going here, the 3 going here, and the 5 wouldn't move. So the reason they call it an insertion sort is we inserted the 2 bumping over everything up to where the last thing was. Yeah, and in this case, sort of boring because then we're done. Technically, the algorithm would look at the 5 and it would go back and see, should 5 go here? Should 5 go here? No? Okay, then I won't move anything. So let's do a bigger one. I got a good one here. So you should write this down. So here's a new set. So the first thing we do, we look at the 2. We look at that 2. That's our current item. And then we go to the left and say, should this 2 be before anything? Yeah, it should be, right? So we put the 2 here, and we move that 5 over there. Meanwhile, the 7, the 3, and the 1, we haven't touched them. They're just sitting right where they were. So that was when we were looking at the 2. And maybe I'll underline the one we're looking at for each one. Right here, we're looking at the 7. And we go back. Should 7 go before the 5? No. Should 7 go before the 2? No. So after a second pass of this sort, it looks like this. And you might say, well, we don't even have to do the pass. Well, we did a pass. We took that 7 and we checked all the way back to the beginning. And then we didn't change anything. So it did execute the code, and you would, if I said, tell me what it looks like after 2 passes, I would want you to show me that. Okay, now we're looking at the 3. And we check. Does the 3 go, is 7? No. 3 go 5? No. Yeah, 3's less than 3. We go, I guess you go all the way until it doesn't, until it's not less than something. You don't just do 3, 7. You go all the way back here to this 5 spot. So 2, 3, 5, 7, 1. And then finally you're checking this 1 and you're saying, hey, I'm going to go to the left until I can't go no more. And then it's 1, 2, 3, 5, 7. So it took 4 passes to do the insertion sort on this data. Questions? Yeah.
So would that be using the dot, like this dot add
Sorry, somebody coughed right when you were speaking.
Last year.
would that be like the list dot add I, comma, E? Like to like the
Yeah, the add where you put an index value on it. Yeah, and you have to be careful with an array list. I'm not going to make you do this with an array list, but if you were doing an array list, you'd have to be careful, because if you did the add, then you couldn't remove it from where it was before, because it already would be a different index. So you might want to remove it and then add it. Yeah, but yeah, exactly. Okay, so what's good about this sort method?
What is it?
There must be something good, because the College Board wants you to learn it. I'll tell you there's two good things. I don't know what happened there. It's relatively easy to code, and it's quick for small data sets. What's not so great? It's very inefficient for large data sets. So if you were, Amazon or Google, you're not using an insertion sort with millions and billions of records, or a bank, or... All right. Now we're going to do the other kind, selection sort. This one is easier to describe, I think. Hopefully it comes through. Start at the beginning and find the smallest element in the whole list. Put it first, swapping locations. Swapping with... So for this one, you're not inserting and moving a bunch of things. You just start at index 0, go through the whole list, find the smallest thing in the whole list. And if it's not already at item 0, trade places. So take the first one, even if it was the last one. If say whatever it was, go find the smallest item, trade places. The current item and the smallest item in the list. Then you move your pointer to index 1. And you go through the whole rest of the array. Find the smallest thing in the whole rest of the array, and if necessary, trade places, and so on. So you're leaving behind yourself a sorted bunch of data. I don't mean sorted, S-O-R-D-I-D, but S-O-R-T-E-D, as you're moving forward. I'll show you. So here's our start. So the one we're looking at is 8. And so we go through the whole list. What's the smallest number? 0. So now we're going to trade places, the 0 and the 8. So after one pass, it's 0 first. 6, 7, 5, 3, 8, 9. That's one pass. And now we know we're sorted at index 0, so we're going to look at index 1.
How do you underline the numbers?
I'm just doing Control U, but I'm in Word. But I bet Google does that.
Doesn't work in Notepad. Well, I'm on Notepad.
There's no underlining in Notepad. All right, so we're looking at 6. We go through the whole list, find the smallest number. I mean, it could be that it was 6, but it turns out we find it 3. So now we're going to put 3 where the 6 was. So we have 0, 3, the 7, 5, don't change. The 6 is here. And like the human part of you might be thinking, did we really have to put things like in the wrong place, like when we know, like why don't we just move the 7 because we can see it. But you remember, computers, you have to give them a rule, and this algorithm, they're going to go ahead and one thing at a time. Okay, so now we're looking at the 7, that's our current item. So we're going to go through the whole list, find the smallest number that's to the right. In this case, it's a 5. So in this case, we're just swapping those two. 0, 3, 5, 7, 6, 8, 9. And now our current index is that 7. We look for the smallest thing to the right, and it's the 6. 0, 3, 5, 6, 7, 8, 9. And I think we're done, right? Yeah, so again, it took 4 passes with this data set, but imagine multiplying this by 1,000. It's not, it gets gnarly. I mean, for the data sets we'll be doing it, it wouldn't matter. But this has the same issues. I'm going to copy these paragraphs and put them down there because it's the same pros and cons. So what's good about a selection sort? It's easy to code, and it's quick for small data sets. Relatively easy to code. I mean, it's not trivial, but this one I think is easier to code than this insertion sort. Yes, sir.
Merge sort is not the only logarithmic sorting algorithm. Quicksort
I believe
is
you.
on average logarithmic, and heap sort is also logarithmic.
Awesome. I learned something new from you. So in Unit 10, we're going to learn about the merge sort method, which uses recursion to sort things faster. What's what? Merge sort.
And quicksort.
And Yasha's favorite sort, a quick sort.
Well, quicksort implemented properly is 2 to 3 times more efficient than merge sort.
Oh, wow. Awesome. A merge sort is the one we'll learn. We won't probably see the code, but I'm sure you could look it up online. It's kind of black magic.
The others are really complicated ones.
All right, I got a little half sheet I want you guys